Okay, it's 9:06. Let's start. So today's topic of discussion will be linear discriminant analysis. And before I could start LDA, let me just give you a brief, quick recap of the things that I wanted to discuss yesterday, but I wasn't able to because of lack of time. So there are few things in principal component analysis which tell us as how do we make decisions on how many principal components to drop and which of the principal components we should drop. So in this regard, I have some of the sections which I will discuss today. So as you know, in last class, I discussed about how principal components are calculated. What are principal components? So basically, principal components are nothing but the projection of your data points on a new coordinate axis in a new direction. Okay, so initially if I talk about original data matrix, the original data matrix is in this direction, x1 and x2. However, our spread, the variance is in some other direction. So what we do using the eigenvectors and eigenvalues, we try to find out the new coordinate system which we call as principal axis, the new directions, and then these principal axes become the new coordinate system. When we take the projection of original data onto new coordinate system, those values become the principal components. As many variables you have in the original sample, that many variables will be created again, and that many principal components will be created again, and it's your responsibility to decide which principal component to keep and which principal component you want to discard. It starts from first principal component and goes downwards. So first principal component is the most important one, which also has the maximum variance explained. Okay, so what do we mean by maximum variance explained? I'll just discuss that, and then before that I will discuss how do we decide which principal component to drop, and then I'll explain what is variance explained. So there are arbitrarily three methods which we normally undertake in deciding which principal component to drop. The first method I discussed yesterday, in which I actually showed you that we keep on increasing the principal component. Like over here, when I run this code, you see it takes one PC at a time. So at first principal component, the accuracy is 54%. When I add the next principal component, the accuracy is 71%. When I add the third principal component, the accuracy is 72%, and so on. So finally, among these, you have to decide, and you will be the best judge to decide how many principal components you want to keep and which principal component you want to discard. That is the safest and easiest method. However, it takes huge amount of time. The other methods are like calculate the proportion of variance explained. Okay, first we find out how much variance is being explained by the principal component. When we talk about proportion of variance explained, I will just move on to that, but before that let us see how do we utilize proportion of variance explained. For a feature, pick a threshold. So suppose a principal component is explaining 52% variance, and then I add another principal component, and adding 2 I get 72% variance. Then we say that if our threshold is 80%, then we will say that okay, add one more principal component. Let's say another principal component adds few more, so that we have 75% variance explained. Then add few more up to the limit that we have at least 80% of variance explained. As soon as we get this 80% variance explained, then after that we can ignore the remaining principal components. That is a rule of thumb. So what it says calculate the proportion of variance explained for each feature, pick a threshold. Okay, pick a threshold and add features until you hit that threshold. For example, if we want to explain 80% of total variability possibly explained by our model, add features with the largest explained proportion of variance until your proportion of variance explained hits or exceeds 80%. Okay, because because each eigenvalue is roughly the importance of its corresponding eigenvector, the proportion of variance explained is the sum of eigenvalues of the feature you kept divided by sum of eigenvalues of all feature. Right. So adding the PCs is going to add more variance explained. But then what is variance explained? I'll now move on to that, and we will discuss with an example. So in case of PCA, variance means summative variance. Okay, although multivariate variability or overall variability, these are the terms which are normally used. Now we give a covariance matrix of three variables. Okay, and their variances are on diagonal, while this covariance is given on the non-diagonal uh, positions. So their variances are on diagonal, and the sum of three values, that is 3.448, is the overall variability or the total variability. So you see we have three PCs over here. Okay, principal component analysis replaces original variable with new variable. So this was the original data, and this is the covariance matrix of original data. When we performed principal component analysis on this covariance matrix, we obtain a new covariance matrix such that now we have these three values on the diagonal, which are 1.6513, 1.22028, and 0.576843, and so on. So we have these three values. Now the interesting thing is, in the original data matrix, the covariance matrix has a variances of a overall variability of 3.448, and that is obtained. This value 3.448 is obtained by adding 1.34, 0.619, and 1.4855. If you add these three diagonal values, you will get the overall variability of the original data matrix. And what is this data matrix? This matrix is the covariance matrix of the original data matrix. So if I add all the diagonal values, I will get the total variability of the data matrix. If we perform principal component analysis on this covariance matrix, we will get a new covariance matrix such that it will not have variance. Okay, all of them will be, this is a variance. Okay, this is not this is a covariance matrix. However, this is the variance. This is the variance. This is the variance. And covariance in the matrix, covariance matrix after performing PCA becomes 0. So any non-diagonal element will have a value of 0. Okay, because they are, all the principal components are independent of each other. That is why we do not find any covariance in this covariance matrix. Only elements which are there on the diagonal will have some variance among themselves. So the unique property of performing this PCA over this covariance matrix is that if you original matrix, if you add the values of diagonal, you got 3.448. However, again, if you add the values on the diagonal, the element values, you will again get the 3.448 value. That is a very interesting property. Okay, that can be proved also why it is like that. So now the diagonal sum is still 3.448, which says that all three components account for all the overall variability of the data. But so I have three principal components. Originally there were three variables. Now again we have three principal components. So three principal components account for all the variability of the multivariate variability, total variability. That is 3.448. Now, out of 3.448, which principal component has got the maximum percentage? Okay, so the first principal component has a variability of 1.651. Okay, so what we say, how much percentage is 1.651 of the total variability that we can easily calculate by dividing 1.651 by 3.448, the total variability, and taking a percentage, and that accounts for 47.9%. Okay. So first principal component explains what we say over here. First principal component explains 47.9% of the overall variability, and in other terms, the 47.8, roughly 48% of variability of the original data is due to first principal component only. Okay, because you see, the concept behind principal component analysis is to find out maximum variance. That is what I actually explained yesterday also. I'm looking for maximum spread of the data, maximum is variance. So the maximum variance is explained definitely by the first principal component, because that is the most prominent principal component. So obviously and intuitively, the first principal component will have maximum variance explained. So evidently we get 48% of overall variability being explained by the first principal component only. That is 1.651 divided by 3.448. Now the remaining principal component out of 48, so we are left with 52% of variance. Now let us take the second one. Second one explains 1.220 divided by 3.448. That's equal to 35.4% of variability, overall variability, right? So if I add the first and second, I will get somewhere around 82% variability. Okay, 82%. It's 9, so 83%, near about 83% of variability has been explained by first and second principal component only. So I don't actually need the third principal component if my threshold is 80%. If I need only those principal components with which I could explain 80% of variance, then in this case I don't really need the third variance. Okay, so this is what is meant by variance explained. So what do they mean when they say PCA maximizes variance? PCA explains maximum variance. That is not, of course, that it finds the largest variance among three values. PCA finds in the data space the dimension, okay, the direction with the largest variance out of the overall variance. That largest variance would be 1.651. Then it finds the dimension of second largest variance orthogonal to the first one. That becomes the second PCA out of the remaining, right? The second dimension would be 1.2202 variance, and so on. The last remaining dimension is 0.57 variance. Okay. So we understood what is the second method of finding out how many PCS to include and how many PCS to drop. So you put a threshold of 80% and keep on adding PCS until you reach this threshold of 80% variance explained. Now this 80% is totally user dependent term. It's your choice, whatever number you want to keep over here. The third uh, method is using a scree plot. Okay. Now here we calculate the proportion of variance explained for each feature. We sort features by proportion of variance explained, and then we plot the cumulative proportion of variance explained. This plot is called scree plot. One can pick how many features to include by identifying the point where the next feature has a significant drop in variance explained relative to the previous feature, and thus we choose this feature. Up to this point we choose the number of features. Like over here you see a scree plot is given above. The red line indicates proportion of variance explained by each feature. So you see the first feature PC1 explains the maximum variance, then second one, and then there is a sharp decrease at the after PCA2 and PCA3. However, from PCA3 we see that is a very small change, although if we calculate PC3 versus PC13, definitely there is a significant difference. However, still the gradual change is very minimal. So the red line indicates the proportion of variance explained by each feature individually, which is calculated by taking their principal component's eigenvalue divided by sum of all eigenvalues. Thus, the proportion of variance explained by including only principal component 1 is lambda 1 upon sum of all lambda values, which is about 23%. The proportion of variance explained by including only second principal component is lambda 2 upon sum of all lambda, which is again about 90%, 19%. The proportion of variance explained by including both principal component 1 and 2 is lambda 1 plus lambda 2 upon sum of all lambda values, which is about 42%. And this is where the yellow line comes in. The yellow line indicates the cumulative proportion of variance explained if you have included all principal component up to that point. So for example, the yellow dot above PC2 indicates, if I just unzoom it, you see. So the yellow dot above PC2 indicates that including principal component 1 and 2 will explain about 42%. So if I could annotate, you see, if I could add PC2, if I just draw this line, okay, the point above PC2 is somewhere up to 42%. Okay, so explains 42% of variance. Now after this, uh, so you see here, if we have after two principal components, first and second, we see that there is an elbow being created in this plot. Okay, the cumulative variance, we see an elbow kind of being created over here, such that after this point we see an elbow being created over here. So you can observe with discrete plot where you get this elbow. As soon as you obtain this elbow, then you can very safely determine that after this principal component, the remaining principal components are not giving a significant increase in the variance explained, overall variance explained. So you can safely remove all the features after this point. So these can be ignored. Okay, this is what is the use of discrete plot, and this is how we observe the pattern of change, cumulative various proportion of overall variance explained, to identify which feature to keep and which feature to drop. Now that concludes our principal component analysis overall picture. Now from here I will move on to linear discriminant analysis, and then yeah, linear discriminant analysis is also very close to principal component analysis. However, there is a unique difference between linear discriminant analysis and principal component analysis. You understand, I hope, with the last two lectures that I have taken and with the sessions that we have been doing, you must understand that whatever we are discussing over here, we are all the time talking about the steps that we take before we create the model, mathematical model, or that's the machine learning algorithm model. So before we take up the machine learning algorithm model creation, we have to get our data in the proper shape. So for that, we have been doing dimensionality reduction. The first algorithm we discussed was singular value decomposition. The second algorithm that we discussed is principal component analysis. I concluded principal component analysis today itself. Now, this is the third method, linear discriminant analysis, which is also one of the most used dimensionality reduction techniques in the pre-processing step of pattern classification and machine learning applications. However, all these three algorithms are projection-based algorithm. When we talk about projection-based algorithm, what we really mean by that is You have the whole data, and data should be in the numeric format. That is one of the requirements. So you have the data and you don't really use that data. What you do, you project it onto a lower dimensional space. Okay. Lower dimensional space means it's actually a very straightforward statement. When we say we have huge dimensional space, our search space is multi-dimensional. What do we really mean by that? As I told you yesterday also, if we have two-dimensional space, it means we have two features and we are searching in a plane. We are searching for the optimum solution in a plane. If we add extra dimension, means if we add extra feature or variable, then we are adding extra dimension to the search space. So from two-dimensional search space, now my search space has become three-dimensional. And if you imagine, if you are sitting in front of a table, you try to imagine that two-dimensional space was the tabletop. However, as soon as you added the third dimension, this became the volume. Okay, so this volume would uh, immediately the third dimension is perpendicular to the tabletop, so it will protrude out of the tabletop and will become the, instead of becoming the area, or you can imagine it to be the floor of the room. Earlier when it was two-dimensional, it was the floor of the room. Now it has become the whole room. Okay, so I have added extra dimension. With just adding extra third dimension, I have created such a huge volume in which I have to make our search for the optimal solution. Similarly, if you add another dimension, the fourth dimension, which is again perpendicular to the three dimension already existing dimensions, we as a human being are not able to visualize what that dimension would look like, but still, just for the sake of understanding, we imagine that there is a fourth dimension. So with the change that we observed from second dimension to third dimension addition, the increase in search volume. Similarly, you can imagine the increase in search volume when we add extra dimension. So as many variables, as many features as you want to add will only add up the number of dimension, and with the increase in number of dimension, the search space that you have to actually implement your search in increases exponentially. Okay, so and that was the curse of dimensionality. So with this problem, when we have a multi-dimensional data, like most of the images that we obtain are huge images. Okay, similarly, if we obtain video data, again the dimensionality is huge. So what we should do is first reduce the dimensionality, because a lot of information over there is such that we don't really need it, or probably they might not be having much effect on the overall result of the algorithm. So our job is to, first we have the data, proper data, then our job should be to reduce the dimensionality. When we say we are reducing the dimensionality in the mathematical term, vector space term, we imagine it to be a data point which is present in a high dimensional space, let's say 100 dimensional space, and from 100 dimensional space I am trying to project that data onto a two dimensional or three dimensional data space. Okay, so our job is to reduce these 100 dimensions to three dimensions only. Okay, although it might seem as if we are losing a lot of data, a lot of information, a lot of knowledge. Definitely we are losing a lot of knowledge, but that knowledge is not very significant in terms of the answer we are trying to find out. That is why we project our data from higher dimensional space to lower dimensional space. So if we project it onto a lower dimensional space, the values that were there originally will definitely change, right? So suppose you had this GPA as the example I am carrying from last day. Again, if you want to predict the GPA of a student in the next semester, you have a value of GPA in the previous semester. That value was suppose 8.5. So if you project this 8.5 from 100 dimensional data space onto a two dimensional data space, this 8.5 will definitely change to some other value. Okay, so all the feature values will be projected will be changed and projected onto a smaller dimensional data space. So all values will change. Their interpretation will change such that initially with the original data matrix, you are able to interpret that 8.5 means out of 10, he has obtained 8.5 pointers. But now 8.5 might become 0.36 something or 0.85 or 0.2737 something like that, which you will not be able to explain or relate even, okay, with the physical world. But that data has been projected, okay. That data still carries all the properties of original data matrix, but the value has been changed and the value has been projected onto a lower dimensional space. Now if we are in the lower dimensional space, suppose we are in three-dimensional space, then easily we can visualize the whole data matrix and we can see the properties of the data matrix. So in all three algorithms that I discussed, and I'm still in the process of discussing the LDA, we are projecting our data from a higher dimensional space onto a lower dimensional space, and we are creating an approximate data matrix. Okay, so the original data matrix is being approximated such that the new approximated matrix is belonging to a smaller dimensional space, has lesser number of dimensions, has lesser number of features. So again, LDA is another projection based algorithm. Okay, so the goal is to project a data set onto a lower dimensional space with good class separability in order to avoid overfitting. Right? In PCA, we actually wanted to have maximum variance. In LDA, we want to have maximum separation. That we will see. So just read through. Ronald Fisher formulated the linear discriminant in 1936, the use of multiple measurements in taxonomic problems, and it also has some practical uses as classifier. The original linear discriminant was described for a two-class problem, and it was then later generalized as multi-class linear discriminant analysis or multiple discriminant analysis by C.R. Rao in 1948. The utilization of multiple measurements in problems of biological classification, that was the finding of Dr. C.R. Rao in 1948. The general LDA approach is very similar to a principal component analysis, but in addition to finding the component axes that maximize the variance of our data, we are additionally interested in the axis that maximize the separation between multiple classes. That is the fundamental of linear discriminant analysis, LDA. So I'll just read it again so that you so as to emphasize upon the fact that how we are different from PCN. In finding the component axis that maximize the variance of our data, that was job of PCA. Here in LDA, we are additionally interested in the axis that maximizes separation between multiple classes. So in general, dimensionality reduction does not only help reducing computational cost for a given classical task, but it can also be helpful in avoiding overfitting. Okay, now you see how it is these two are different. Both LDA and PCA are linear transformation techniques that are commonly used for dimensionality reduction. PCA can be described as an unsupervised algorithm since it ignores class labels and its goal is to find the direction, the so-called principal components that maximize the variance in dataset. However, in LDA is a supervised algorithm and computes the direction that will represent the axis that maximizes the separation between multiple classes. So we have to supervise such that this separation is maximum. So with the help of this diagram, I think it will be able to understand. Then PCA component axis that maximize the variance. So we are trying to find the component axis which maximizes the variance. However, in LDA, our objective is to find this separation. So you observe over here, we have got two two classes. So one class is like this, you see, one class has a positioning of this and another class variables have positioning of this, right? So it gives the maximum separation between centroid of two features, right? So if we project in this direction, it will be bad projection because it is not separating. All the values are falling in this region only. But this projection on this axis will be a better projection. However, you understand that this is giving the maximum variance, right? So vertical direction is giving me the maximum variance in this direction, vertical direction. But horizontal direction is giving me good separation, this variance and this variance. So I have to observe, it needs to be supervised. This needs to be supervised that the axis that we choose gives us clear cut separation. Even if it is not clear cut, at least a good separation between the two classes. It might sound intuitive that LDA is superior to PCA for multi-class classification tasks where the class labels are known, but this is not always the case. Comparisons between classification accuracies for image recognition after using PCA and LDA show that PCA tends to outperform LDA if the number of samples per class is relatively small. However, if the number of sample per class is larger, LDA tends to perform better than PCA. And it is not uncommon to use both LDA and PCA in combination. That is, perform PCA for dimensionality reduction and immediately after that you perform LDA as well. Okay, so on the original data, just to get a good feeling. Now, we will summarize LDA in 5 steps. LDA, the first one is compute the d-dimensional mean vector for different classes for dataset. Now, what is mean vector? Every feature, for every feature, we will calculate the mean vector. Okay. So I'll start from here and then without skipping the topic, let's assume that our goal is to reduce the dimension of a d-dimensional dataset by projecting it onto a k-dimensional data space where k is definitely less than d. We want to reduce the number of dimensions. So how do we know what size we should choose for k? K is the number of dimension of the new feature subspace. And how do we know if we have a feature space that represents our data well? So for that, the question is, how do we know what is a good feature subspace? We will compute eigenvectors, the component from our dataset, and collect them in so-called scatter matrix. Okay. So you see, in all the three algorithms, we have been dealing with eigenvalues and eigenvectors only. Okay. So for this purpose, I had actually imagined that I assumed that all of you would have a clear cut understanding of what are eigenvalues, what are eigenvectors, and how to compute them for a given matrix. Okay. So that's why I didn't get into detail of calculating eigenvalue and eigenvector that you can obtain from any good mathematical book or there are a lot of articles even on internet with which you could understand what are eigenvalue, what are eigenvectors. However, if you are really interested, I have a very good link that I would really want to share with you. I think it's in the just a moment. It's a 1B, one blue, one three brown. uh, That 3B, 1B series, right? So if you get on this video series by 3 blue 1 brown series on eigenvector and eigenvalues, he gives you a very good explanation of through animations. He gives you a very good explanation of what is eigenvector, what is eigenvalue, And in fact, this series of Essence of Linear Algebra gives you a very good introduction to linear algebra topics that are required for understanding the linear transformation basis, all these things. So I would definitely hope that you would go through this video, and this video is extremely beautiful video, right? So getting back to our topic, so we will compute eigenvector for our from our data set and collect them in so-called scatter matrix. Okay, so we will create two scatter matrix in between class scatter matrix and within class scatter matrix. Kind of intra-class and inter-class scatter matrix. Each of these eigenvector is associated with an eigenvalue, which tells us about the length and magnitude of the eigenvector. Okay. If we would observe that all eigenvalues have a similar magnitude, then this may be a good indicator that our data is already projected onto a good feature space. So this is the basis with which we say that our data is in a good feature subspace. When the eigenvalues have similar magnitude, if we observe that all eigenvalues have similar magnitude, then it is a good indicator that our data is already projected onto a good feature space. In the other scenario, if some of the eigenvalues are much larger and as compared to other, we might be interested in keeping only those eigenvectors which have the highest eigenvalues, since they contain the most information about our data distribution. Vice versa, eigenvalues that are close to zero are less informative, and eigenvalues which are having the most eigen magnitude are the having the most information. So the eigenvalues which are close to zero, we must drop them and construct new feature subspace. So this gives us a feeling of how do we find out whether our subspace is good or not. If eigenvalues are of similar magnitude, the feature space is a good feature space. Now, how to perform LDA? LDA can be performed in 5 steps. First, we compute the d-dimensional mean vector for different classes from the data set. So for every class, okay, we have d-dimensional mean vector for every dimension. We calculate the mean and then we calculate the vector for those many classes. Compute the scatter matrix. We calculate two scatter matrices in between class scatter matrix and within class scatter matrix. We compute eigenvectors even e2 ed and their corresponding eigenvalues lambda 1, lambda 2, lambda d for these two scatter matrices. We sort the eigenvectors by decreasing eigenvalues in the order of decreasing eigenvalues and choose first k eigenvectors which are having the largest eigenvalues. Okay, we create a d by k dimensional matrix W where every column represents an eigenvector. Okay, just like the principal component analysis. However, in principal component analysis, we were creating the we were finding eigenvector eigenvalues of what? Of the covariance matrix. However, over here, what we are doing, we are calculating two matrices, scatter matrices. These are in between class scatter matrix and within class scatter matrix. And then we are finding the eigenvector and eigenvalues of these two matrices. Then we are sorting the eigenvector by in the decreasing order of eigenvalues and choose first k. What will be the number of k? That again is we have seen how to find out k. Okay, k is the number of eigenvectors that you are going to retain. So if d is say 100, d is 100 and you want to keep 10 features only, then k will be 10. And how do you decide the value of k? That we have just seen that if either you choose principal components one at a time and then see how much accuracy is increasing, or you choose the variance explained, or you implement the scree plot and find out the elbow Okay, so these are various methods with which you could decide upon a value of k. And mathematically, you can also actually explain in the paper that you write that these are the methods with which you came up to a value of k. So out of 100, if d equal to 100 means originally there were 100 dimensions and you want to retain only 10 dimensions, so k will become 10. Okay. So sort the eigenvector by decreasing eigenvalues and choose k eigenvector with the largest eigenvalue to form a d by k dimensional matrix. Use this d by k eigenvector matrix to transform the samples onto new subspace. Now this has become a coordinate system kind of thing. It will give you a new coordinate system in which you want to project your original data point. So what you'll do, use this W to multiply to the original data matrix. So what we do over here, this is my original data matrix X. I will multiply this with W so that I will get a projection of original data points onto the new coordinate system. So W is giving me new coordinate system. If I multiply it with X, I will get all the projections of original data point onto the new coordinate system that will be get by W. So use this d by k eigenvector matrix to transform the samples onto the new subspace. So we have projected our data samples from a higher dimensional space to a lower dimensional space, where lower dimensional space is given by capital W matrix, where X is an n by d dimensional matrix representing n sample and Y are the transformed n by k dimensional samples in the new space. Y, it should be capital Y actually. Y. Okay, Y are the transformed n by k dimensional samples in the new subspace. Let's see. We will do an example and then we will see how do we perform LDE. We are going to use the iris dataset from UCI machine learning repository. We all know we have been doing iris. I think this is the hello world of machine learning where we deal with iris dataset. We have three classes: iris setosa, versicolor, and virginica. All of them have got 50 samples each, so total of 150 samples are there. And then there are four features: sepal length, sepal width, petal length, petal width in centimeters. This example shows what is petal. So this is the petal and this is the sepal. So the length and width of these three classes. So we have created a feature dictionary in which we have the label, sepal length in centimeter, sepal width in centimeter, and this is all. So if I just connect it so that I could run it. Now I'm going to read this into our data set. We create a data frame with the pandas library. We can read the CSV file from this. Okay, sorry. All right. So we have created this feature dictionary in which this will be the headings. And now we have these samples. If I see the tail, the last five samples, the last five samples look like this: sepal length in centimeter, this, sepal width in centimeter, this, sepal petal length and petal width in centimeter. And then finally we have the class label Virginica for all of them. Okay. So having it, since it is more convenient to work with numerical values, we will use the label encode function from scikit-learn library to convert the class labels into numbers, numeric values, 1, 2, or 3. So this is what we do. We import the label encoder, and for all the data frame columns, what we are going to do we are going to use the feature dictionary items, and then we take the class label and convert it to 0, 1, 2, 3 values. Okay. So yeah, and then we know that 1 is identified as setosa, 2 is versicolor, and 3 is virginica. The histogram and feature selection we see just to get a rough idea of how the samples of our three classes W1, W2, W3 are distributed. Let's visualize the distribution of four different features in a one-dimensional histogram. So just to get this histogram, See, we have done it on the basis of four features. There are four features, right? So which feature gives us the what kind of pattern that feature gives us is very visible from this diagram. That is why some of the times visualization is so important, that it gives you a very nice idea of how to proceed with the mathematical model that you are going to create. So in this example, you see with this visualization, in which what I have done, I have just to get a rough idea how the samples of our three classes are distributed. We visualize the distribution of four different features in one dimensional histogram. So individually, all the four features are plotted over here. You see sepal length in the first block, sepal width in the second block, petal length in the third block section, and the petal width in the fourth block section. In the sepal length, you see all these colors are mixed together. Okay, there are three classes: setosa, versicolor, and virginica. All of them are mixed among each other. Again, the same thing is there for sepal width also. All of these classes, all of these samples are mixed together. While in case of petal length, there is a very clear cut distinction between setosa and remaining ones, means versicolor and virginica. So setosa is clearly distinguished as soon as I take up the petal length. So in case of LDA, this is our objective, that we want to have a kind of distribution or the feature space with which we are able to create the maximum separation. So with this, this is, and that is why we say LDA is a supervised algorithm, supervised technique in which we are observing the performance of the algorithm. So if we distribute it on the basis of petal length, we observe that this Setosa class has been clearly distinguished. Now, among the remaining two, versicolor and virginica, there's a very small overlap in case of versicolor and virginica, and the same goes for petal width as well. So petal width and sepal width, if you see, in case of petal width and petal length, if we observe the petal width and petal length, we will be very clear in identifying which class of flower iris that is. So either it is, if it is petal width, it's even clearer than petal length. So I think the best distribution is when we distribute it on the basis of petal width, and we get the maximum separation, and that is our objective in classification problem. If we are able to distinguish, and with greater confidence we are able to declare that a sample belongs to a given class, then the model is successful. So just from looking at these simple graphical representation of feature, we can already tell that the petal length and widths are likely better suited as potential feature to separate between three flower classes. Okay. In practice, for low dimensional data, instead of reducing the dimensionality via projection, a good alternative would be a feature selection technique. Okay. So this is what is a professional suggestion. So in low dimensional data, instead of reducing the dimensionality via projection like LDA, good alternative would be a feature selection technique. For low dimensional data set like iris, a glance at those histogram would already be very informative. So when we perform dimensionality reduction, we must be very clear in mind that our dimensions are huge and we are not able to implement feature selection or elimination. Then only we should go for projection based mechanisms. So the 5 steps I discussed above, let us compute them and see how they function. So first step was computing the d-dimensional mean vector. So in the first step, we will start off with a simple computation of mean vector. How many classes we have? We have 3 classes. For all 3 classes, for 4 features, we are going to create. So mi class 1, let's say color setosa, let's say for setosa I equal to 1, iris setosa. Setosa has 4 features, so 4 means would be calculated mean 1 for sepal length, mean 2 for sepal width, mean 3 for petal length, and mean 4 for petal width. And similarly, I M1, M2, M3, three vectors will be calculated. So we have computed over here three mean vectors. Now with this code, we computed three mean vector for class 1 is this, vector for class 2 is this, vector for class 3 is this. Now, a quick note on standardization, which I find important to discuss over here, is that feature scaling, such as standardization, does not change the overall result for LDA. Okay, so it may be optional. The scatter matrices will be different depending on whether the features were scaled or not. Of course, the matrix that we have, this diagram also will be different if we standardize or scale. However, the overall result will not be affected much. However, the important part is that eigenvalues will be exactly the same as well as the final projects. The only as well as the final projections. The only difference you will notice is the scaling of component axis. Okay. So second step is computing the scatter matrix. For this, we will compute two scatter matrices, the within class scatter matrix and between class scatter matrix, kind of within class, intra-class or inter-class scatter matrix. Within class scatter matrix, we have two methods in which the first method within class scatter matrix SW is computed by following equation. SW is a summation on C classes of SIs, where SI is given as for all samples in the d-dimensional space x minus mi, x minus mi. Okay, where mi is the mean vector for a given uh, class and mi is the mean vector. So this we have already computed. So using these formulas, we can calculate the within class scatter matrix like this. The code for it is given over here. We have we compute the class, and within class scatter matrix we get this scatter matrix. Okay, the other method is in which we could also compute the class covariance matrices by adding the scaling factor of 1 by n to the within class scatter matrix, so that our equation becomes 1 upon n minus 1, and this is the formula for Si. Okay, so this becomes the SW will become summation ni minus 1 sigma I. Okay, so if we get this ni minus 1 over here, that becomes the SW, where ni is the sample size of respective class. Here we have 50, and in this particular case we can drop the term ni minus 1 since all classes have the same sample size. Okay, the resulting eigenspace will be identical eigenvectors, only the eigenvalues are scaled differently by a constant factor. The within class scatter matrix is actually calculated with this formula ni mi minus m into mi minus 1 transpose. The between class scatter matrix SB, the m is the overall mean, mi and ni are the sample mean and sizes of the respective classes. Okay. So with this code, we can calculate the between class scatter matrix, and this is what we have obtained over here as the between class scatter matrix. The third step is to solve these two matrices for obtaining the eigenvalue and eigenvector. Okay, so now this has become solving the generalized eigenvalue problem for the matrix S inverse. Uh, am I audible clearly?
Yes, sir. Yes, sir.
Okay, okay, fine. Actually, it was showing me I rejoined, so I thought probably I was disconnected.
No, 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 sir. It's clear.
Okay, thank you, ma'am. So solving when we solve the generalized eigenequation, we have to solve this matrix. For this matrix, we are going to so these are the two matrices within class and between class. So we will create a new matrix S inverse within S inverse within will be an inverse of the within class scatter matrix multiplied by between class scatter matrix. So we will get one matrix for which we are going to find out the eigenvalue and eigenvectors. Okay. We will solve the generalized eigenvalue problem for the matrix this to obtain linear discriminants, and these are the eigenvectors, right? So we obtain first eigenvector, and see, although we can discuss a lot of ways in which we can mathematically find out eigenvector and eigenvalues. However, you have this linear algebra library function eigen, with which you can very easily find out eigenvalues and eigenvectors. Okay, so in our classes we emphasize upon our students to compute the eigenvalue and eigenvector by hand. However, in programming, you don't have to worry about too many things. This linear algebra, the numpy linear algebra function eigen will give both eigenvalues and eigenvector for the matrix that you have. Okay, so here itself you see we are passing SW matrix, the within class matrix, and then this linear algebra INV function, that is inverse function. If I just put it over here, this is the inverse function which computes the inverse of a matrix. So we find out inverse of SW matrix over here. So this part is calculating inverse of SW matrix. Then we take a dot product of this matrix with the SP matrix. The resultant matrix is being passed on to EIG function to compute the eigenvalue and eigenvectors of the matrix. So we obtain eigenvalue and eigenvectors, and then we print them to get eigenvector 1, eigenvector 2, eigenvector 3, 4, and then corresponding eigenvalues. Right? Now, depending on which version of NumPy and later algebra package we are using, we may obtain the matrix W with its signs flipped. Okay. So please note that this is not an issue. If V is an eigenvector of matrix A, we have AV equal to lambda V. Here lambda is the eigenvalue and V is also an eigenvector that has the same eigenvalue. So if V becomes negative, it will be negative on both sides. When subsequently it will be A minus V will again be lambda minus V. So that will not be an issue. After this decomposition, our square matrix into eigenvector and eigenvalues, let us briefly recapitulate how we can interpret those results. As we remember from our first linear algebra class in high school, college, both eigenvector and eigenvalues are providing us with information about the distortion of linear transformation. Distortion, right? The eigenvectors are basically the direction of this distortion, and eigenvalues are the scaling factor for the eigenvectors that describe the magnitude of distortion. And we are performing LDA for dimensionality reduction. So in this case, eigenvectors are important since they will form the new axis of our feature subspace. The associated eigenvalues are of particular interest since they will tell us how informative the new axis is. Okay, so any axis, the eigenvalue of that axis will tell us how informative that axis is. So if the eigenvalue is larger, the axis is more informative. If eigenvalue is smaller, the axis is less informative. And what do we mean by axis? Axis is the direction, okay, of the transformation, the distortion that we are performing in our original data matrix. So we have a okay, so we have already calculated our eigenvalue and eigenvector, so I'm not getting into it. It's just the same thing. Okay, just reassuring ourselves that what we have calculated is fine. Now we select linear discriminants for the new feature subspace. What we are doing, first we sort it in the decreasing order of eigenvalues. In order to decide which eigenvector we want to drop for our lower dimensional subspace, we take a look at the corresponding eigenvector eigenvalues. Roughly, the eigenvector with the lowest eigenvalues bear the least information about the distribution of data, and those are the ones we want to drop. So what we are doing, we are sorting them in the decreasing order, and this is the decreasing order. The first eigenvalue is 32, second is 0.27, third is 10 to power minus 14 minus 15. In fact, these two, the last two should be 0. However, just due to floating point error, they are still not 0, but assume them to be 0. We can already see that two eigenvalues are close to 0. Right? This is due to floating point imprecision. In fact, these two last eigenvalues should be exactly 0. In LDA, the number of linear discriminant is at most C minus 1, where C is the number of class labels. So you remember this thing very clearly, that we have C classes. So number of linear discriminant can at most be C minus 1. How many classes do we have? We have 3 classes. So we will have only 2 linear discriminants. And since the in between scatter matrix SB is the sum of C matrices with a rank 1 or less. So now let's express the variance, explained variance as percentage. So first one is explaining, again you see I'm taking the same concept of how many linear discriminants we should select and how many we should drop, and for that I'm again taking the cue from variance explained. So first eigenvalue explains 99.15% of overall variability. The second one explains 0.85. So if we add the first and second, we get the 100% variance explained. So we don't need to take any more feature than the first two features. The first eigenpair is by far the most informative one, and we won't lose any information if we choose. Choosing k eigenvector with the largest eigenvalue, we have decided that our k over here is going to be 2. So after sorting the eigenpair by decreasing eigenvalue, it's now time to construct our k by d dimensional eigenvector matrix W. So here it will be 4 by 2 based on two most informative eigenpairs. So our, and thereby reducing the initial 4-dimensional feature space into 2-dimensional subspace. Now how do we form our W matrix? It should be formed from the eigenvectors of the corresponding eigenvalues. Where are the eigenvectors? This is the eigenvector, the first eigenvector corresponding to eigenvalue 32. So this is the first eigenvector and this is the second eigenvector. So if we concatenate these two eigenvector, we will get our matrix W. Now this is our matrix W. The first eigenvector is the first column, second eigenvector is the second column. We get matrix W. Now once we have matrix W, now we have a new coordinate system, right? New axis system, new direction. All I need to do now is to project my original data matrix onto the new directional space, new dimensional space, two-dimensional space W. So for that, as I told you before also, we need to multiply our original data matrix with the new matrix W that we have obtained, and with this we will get a projection of our original data onto the new lower dimensional space, and that will be called Y matrix. X is an n by d dimensional matrix representing n sample, and Y are the transformed n by k dimensional samples in the new subspace. We perform this, and then finally when we plot our data, we see that iris projection onto the first two linear discriminant is like this. So now we, although you will not observe too much of a difference between the feature histogram that we had plotted earlier and this, because it is a very low dimensional data space. It is only 4-dimensional data space, right? So you'll not see much of a change. However, if you do the same on high dimensional data space, definitely you will observe huge change in which the class separation will be very clear to you. There won't be mixing and mergings. It will be very clear, okay, to you. So you see, after plotting this LDA, we get the new, we are plotting the Y uh, matrix. So if we plot the Y matrix, we get LD, LD1, LD2, and we get a very clear separation of the class samples. So through scikit-learn also we can perform the same, and this is the code. You can go through this code. It's just an implementation of those functions, the scikit-learn LDA library. Okay, LDA function. So we have this linear discriminant as LDA. This package gives you the complete control over implementing LDA. So this also you can implement, and that is the end of my discussion on dimensionality reduction. I hope it was fruitful to you. I am now ready to take up questions if you have any. Any questions?
Hello.
Yeah.
Yeah. Myself Devang Pandya from Ahmedabad.
Hello, Devang.
Hello. Okay,
Tell me.
okay, sir. Very nice presentation. You have explained in detail of the CC and LDA.
Thank you.
As this is a completely data driven and data distribution is, I think it is important.
Yeah.
So my question is, PC and LDA, there has been some study that it favors what kinds of distribution, like a Gaussian or some exponential or means any that kinds of thing, which is very important to be aware before we go for PC or LDA kinds of things.
You see, most of the time we want our data to be distributed in the Gaussian order only, Gaussian
Yes.
distribution only, because Gaussian distribution is the one which follows the natural mechanism.
Yes.
Okay, so if Gaussian distribution is the one which follows the natural mechanism, then even if we are not getting a Gaussian distribution, we tend to organize our data, we standardize it, we normalize it so that we get a Gaussian distribution. Why we move towards Gaussian is the natural phenomena of having this distribution in natural activities. So we assume that our data that we have, the number of observations that we have at this point of time is not sufficient enough to give us a natural Gaussian distribution. However, the actual activity represents a Gaussian distribution. Okay, so suppose you have 1,000 samples, right?
Yes.
Although the natural phenomena was actually in a Gaussian distribution, but the 1,000 samples that you have collected, it might be due to any reason, belongs to a portion of that Gaussian distribution. So
Yes.
we can never be sure that the number of samples we have obtained or the number of samples that we have at present is actually a representative of the whole phenomena.
Yes.
So we tend to distribute it in such a fashion that we obtain Gaussian distribution. And once we have Gaussian distribution, then we can be kind of sure. I'm not saying that that is the case 100% of times, but that is the safest way to start uh, further processes. So whatever data set we get, if it is in Gaussian distribution, then we are very confident that it is following the natural phenomena and we have a kind of representation of the whole uh, all possible observations. But if we don't have Gaussian distribution, then we blame it on the lack of observation and we assume that my data set belongs to only a portion of the overall data. So we normalize it, we standardize, and we try to take zero mean unit variance, and then we try to spread it such that it gives us a Gaussian distribution.
Got it.
So we prefer Gaussian in that fashion.
Okay. Yes. So I think there will be certain studies where these methods are also lacking, maybe in case of poison or anything.
Yeah, yeah,
The
definitely.
question is the obvious natural.
Yeah, yeah.
Okay, thank you.
Thank you. Any other question? So I think I will end over here, and next session will start at 10:30, I suppose, right? So yeah, next session will start at 10:35, and we have a test today. So I assume everyone knows about that. It will be from 3:30 to 4, or I don't know. Probably you can message on the chat box, and Dr. Tiwari will be the right person to tell you when he has planned this test. And it is very important. I cannot emphasize enough for you to attend that test and appear for the quiz. Okay, it is very important that you appear for the quiz and pass that quiz. So good luck for the quiz, and I will end my session over here. I hope you were able to gather some knowledge from this FDP and from our lectures. Thank you for being here. Thanks for listening to me, and probably we'll see each other again sometime.